Bismillahirrahmanirrahim. Dear students, in the last lecture, the nonlinear data structure, the trees being discussed along with their types, the binary tree and its various forms were described too, such as complete binary tree, nearly complete binary tree, extended binary tree, and the balanced binary tree. Ladies and gentlemen, in today's lecture, how the binary tree BT is represented in the memory will be explored. Besides this, another type of tree, the binary search tree, will also be explained in today's lecture. Dear listeners, as described in the last lecture, that the binary tree BT is a type of tree in which every node has at most two children or subtrees. That is, the out degree of a binary tree is at most 2. The binary tree is either empty or partitioned into 3 disjoint subsets, such as the first subset contains a single element called root of the tree. The other 2 subsets are themselves binary trees called the left subtree and the right subtree. Such kind of binary tree is depicted in the diagram below. A binary tree T can also be recursively defined as a finite set of nodes such that T is empty, called the null tree, or T contains a distinguished node R, called the root node, and the remaining nodes of T form an ordered pair of disjoint binary trees TL and TR, that is, the left successor and the right successor respectively. Such kind of binary tree is also depicted in the diagram below. Dear students, the binary tree may be represented in the memory in 2 ways, either linked representation or sequential representation. The link representation maintains the binary tree BT in memory by means of 3 parallel arrays, namely info, left and right. And a pointer variable root is also defined. Each node n in the binary tree will correspond to a location k such that the info of k contains the data at the node n. Left of k contains the location of the left child of the node n, whereas right of k contains the location of the right child of the node. Root contains the location of the root of the binary tree. Ladies and gentlemen, if any subtree of the binary tree BT is empty, then the corresponding pointer contains the null value. If the tree BT itself is empty, then the root node will contain the null value. Such values are sketched in the given diagram. Dear listeners, the sequential representation is an efficient way to implement the binary tree BT if it is a complete or nearly complete tree. The sequential representation uses a single linear array with the name tree such that the root R of tree is stored at location 1. If a node n occupies the location k of the tree, then its left child is stored at location 2k of the tree, and its right child is stored at location 2k plus 1 of the tree. The null is used to represent an empty subtree. If the null value is stored at location 1 of the tree, it indicates that the tree is empty. The sequential representation of a tree with depth d will require an array with approximately 2 raised to the power d plus 1 elements. Dear students, there are 3 standard ways in which the binary tree BT can be traversed, and these are pre-order traversal, in-order traversal, and finally the post-order traversal. In the pre-order traversal, the root R is processed first, and then the left subtree of R is traversed in the pre-order sequence. Finally, the right subtree of R will be traversed next in the pre-order. Such pre-order is mentioned along with its binary tree diagram. Ladies and gentlemen, in the in-order case, traversing starts from the left subtree of R, then the root R is processed, and finally the right subtree of R is traversed in the in-order sequence. Such order is also mentioned along with its binary tree diagram. Ladies and gentlemen, in the post-order, the third standard way for traversal, the traversing begins from the left subtree of R in the post-order sequence. Then the traversing of right subtree of R in the post-order sequence is accomplished. Finally, the root R is processed. Such post-order is mentioned along with its binary tree diagram in the slide. Dear viewers, this slide contains the pre-order algorithm deploying the static stack. The pre-order algorithm possesses 4 arguments, namely info, left, right, and the root in its pre-order function call. The in-order algorithm is sketched in this slide that contains a static stack again to accomplish the in-order traversal of the binary tree BT. It also contains info, left, right, and root as arguments of the in-order procedure. Ladies and gentlemen, the post-order algorithm through the static stack is depicted in this slide. The post-order traversal also possesses info, left, right, and root as the arguments of the post-order traversal algorithm. Dear students, the binary search tree is a binary tree such that all the items or key values in the left subtree are less than the root of the binary search tree. Moreover, all the items in the right subtree are greater than or equal to the root of the binary search tree. Each subtree is itself a binary tree. The node with the smallest value is the far left node of the binary search tree, whereas the largest value is found in the far right node of the binary search tree. The in-order traversal of the binary search tree produces a sequenced list. Ladies and gentlemen, the binary search tree enables one to easily insert or to delete elements like the linked list, and to search an element easily like the sorted linear array. It has the complexity of big O log n, which further states that it belongs to the logarithmic efficiency class. A contrast is clearly being made by the binary search tree with the sorted linear array where insertion and deletion is expensive, and with the linked list where search has linear complexity. Dear listeners, to find the smallest element in the binary search tree BST, the left branches must be followed until the null left pointer is reached. Whereas to search the largest node, follow the right branches until the null right pointer is obtained. To insert a node in the BST, the left or right branch is followed down the tree, depending on the value of the new node and until the null subtree is found. Almost all BST insertions take place at a leaf or a leaf-like node. Dear viewers, mentioned in this slide is the procedure to find the location of an item and its parent node in the tree T. Ladies and gentlemen, an algorithm to insert the new item in the tree T is presented in the slide that also calls the find procedure to search the appropriate place in the tree for the new node insertion. Dear listeners, to delete a node from the subtree, 3 cases must be considered to act upon accordingly. That is, in case 1, if the node to be deleted has no children, then n is deleted from T by simply replacing the location of n in the parent node by the null pointer. In case 2, when the node to be deleted has exactly one child, either a left child or a right child, then n is deleted from T by simply replacing the location of n by the location of the only child of n. The third case is for the deletion of a node that has 2 subtrees as its children. To accomplish such deletion, let S of n denotes the in-order successor of n such that S of n does not have a left child. Then n is deleted from T by first deleting S of n from T by using either case 1 or case 2 and then replacing node n in T by the node S of n, which is the in-order successor of n. Dear viewers, the deletion procedure explained earlier for case 1 and case 2 is depicted in this slide. The deletion procedure, ladies and gentlemen, for case 3 is presented in this slide. The case 3 has already been explained previously. Dear viewers, finally, it should be noticed that the 2 procedures mentioned in the last 2 slides may be called in the deletion algorithm of this slide. A quick glance at the deletion algorithm reveals that the call to find procedure helps in locating the position of the node to be deleted. Dear students, in today's lecture, two ways to represent the binary tree in main memory being explored. The binary tree traversing schemes along with their algorithm also being covered. Finally, the binary search tree and its corresponding operations being described. For further details and studies, you are hereby advised to consult the 7th chapter of Data Structures book by Lipschutz. Till next lecture, stay home, stay blessed, and happy reading.